Okay, so good morning, everyone. So first, I will need to explain what happened last Friday. Each semester, I supervise the master thesis for a couple of master students in our department, and this semester, one of them is doing a project. The topic is to say we want to basically hack an encryption scheme by using side channel attack. So to do that, so we need to have some hardware devices. It's basically a circuit board, and so we ordered that device, and that device arrived at the department last Friday. I have to be there. I had to be there to pick it up, and because it was I have to sign on the package and get it and then pass it to the students. So that's why I was not able to teach last Friday. So but what I as I indicated in the email. So don't worry, we will have. So far, we are pretty on track to finish this all the materials even one week earlier, 1 week before the end of the semester. So don't worry about that. And so last week we mainly learned the topic of binary search tree. So if you remember, binary search tree is basically a binary tree is a tree that where each node can have at most 2 children nodes. So in this case, we say this is a binary tree. And then if we got a binary tree and it satisfies the binary search tree property, which is that for every node X is larger than other values in left subtree and smaller than or equal to other values in right subtree, then we call it a binary search tree. So so we learned. So we said that in total we are going to learn 7 functions of the binary search tree, which includes traverse, search, minimum, maximum. So we learned this 4 last week. Okay, so we learned them last week, and so do you remember in traverse we have 3 different orders: in order, pre-order, post-order. By following which order are we going to print out all the values stored in the binary search tree in the ascending order? Which order can help us to print out the values in ascending order?
In order?
Yes, it's the in order. So which is displayed over here in order. If we follow in order, basically we're going for each node we're going to visit its left child and itself, and then its right child. So because of the binary search tree property, we will be able to print out all the values in ascending order. And then we learn the search function. So here, if you remember, we said that in order for us to say here to search for the value 13, we should start from the root of the binary search tree. And then so at the root node, we know that we only need to go to its left subtree because other values to its right in its right subtree are going to be larger than 15, so as to be larger than 13, which is not out of our interest. And then so from after we reach the node that stores the value 6, we'll need to turn right, and then we turn another right. So we'll be able to reach the node that stores the value that we want to look for. So what is the search complexity of the binary search tree?
O of H?
Yes, OH, where H is the height of the tree. Cool. And so for the traverse functions, it's ON because we have to visit all the nodes inside the tree. And then we learned 2 more functions, which are pretty simple: minimum and maximum. So to find the minimum value stored in a tree, we basically need to go from the root. We just need to keep going left, and then so we'll be able to find the node that stores the minimum value. Similarly, if we keep going right, we'll be able to find the node that stores the maximum value of the binary search tree. Okay, so these are the three functions that we learned. Also, we can say that the for minimum and the maximum, the complexity is also OH. Okay, so these are the four functions that we have already learned, and today we're going to cover these two, successor and and insertion function. The deletion function, we will only briefly talk about it because it's too difficult. It's too complicated. If you go to your job interview, no one is going to ask you to implement this one. It's going to take way more time. And so first, let's look at what is the definition of successor. So here, let me use this tree as an example. So again, over here, let's use this tree as an example. So here, if say go a little bit up here. Okay, so here, if I ask you, what is the, if we look at this node, so if we for node X, if we talk about its successor, the successor of node X, successor is basically a node Y that stores smallest value. Larger than X. So here, if this is the node X, it stores the value 7. So what is the successor of this node X? Or basically, what is the value what is the smallest value that is larger than 7?
13.
36.
And 9.
9.
Oh, larger.
Yes, here is it. Okay, this is the successor of X. So because 9 stores, so this node Y stores the smallest value that is larger than 7, which is 9. Right?
Right.
Okay, and then so if we look at another example, so here I'm going to give them some different color. Give them a different color. Let's say we can going to use this is X and this is Y. That Y. Okay. If I'm using a different color, let's say for now, let's say if we look at this node X, if we take this node as X, what is which node is its successor?
Is it X dot left?
X dot no, because here if we check, if we go to its left, then it's going to be the node that stores the value 9. 9 is less than 13. So basically we want to look for the value, the smallest value that is larger than 13. What is the smallest value larger than 13?
$15.
Yes, here. Okay, so this is the smallest value that is larger than 14. So this is the successor of, so for this node X, its successor is basically the root node. Okay, so here I just give you 2 examples to help you understand what is the definition of successor. For the successor of a certain node is basically the node that holds the smallest value that is larger than this node. Yes. Okay. So so this is the definition of successor. Any question with regard to the definition of successor?
So you could just skip like anywhere in the tree. Like it doesn't have to be like the right or left. You could just go wherever it's like the smallest.
Yes, we can. There is, as long as we find the node in the tree, it is fine.
Okay.
So is the definition of successor clear?
Yeah.
Okay, Cool. So so then let's say, how do we find the successor? So here, let's come back to this example again. Here, if we just focus on this node, okay, x. So if x is here, okay, so then basically, so here, we can say that x has a right subtree, right? Correct? It has a right child and also a right subtree, correct?
Yeah, that's right.
This is the right subtree of the node x. Okay, here's it's right subtree. So what we know is that all the values in the right subtree are going to be larger than or equal to x, correct?
Yeah.
So here, this part only stores the values that are larger than or equal to x. So here, because we want to look for the smallest value that is larger than x, basically we only need to find the smallest value over here, right? We just need to look for the smallest value in this part, correct?
Yeah.
Okay. So then so how do we find the smallest value in this part? By just calling the minimum function at this node, okay? If we call the minimum function at this node, it will just keep going left until so there is no more left. And then in that, we will be able to find the node that stores the minimum value, right?
Right.
Yes. Here, if you look, if you don't understand, just look at the definition of the minimum function. It takes a node x, and so while x dot left is not nil, then so it keeps going left. So basically, so for the minimum function, if this is a node x, it will find the so this could be a part of a big tree. Okay, this could be a part of a big tree. If we call the minimum function over node x, it basically will find the smallest value at the subtree whose root is x. Okay, so then here, that's why I say if. So here, what we know is that, okay, if the node x has a right child, we need to call the minimum function over its right child, correct? So in that way, we will be able to find its successor. Got me?
Yeah.
Okay. So let me write it in a more formal way. Okay. So if you understand, so far, any question regarding this statement? If x has a right child, we just need to go to its right subtree and find the minimum value. No? Okay. If no question, then okay. So this is one case. But if we look at this case where we have this node as x, does this node have a right child?
No, it only has left.
No. So it does not have a right child. So then we need to use another strategy to find its successor. Okay. So here, since it does not have a right child, can we go to its left child to find the successor?
Yes.
Yes or no?
Yes.
No. If we go to its left child, if we go to this part, its left child, we will only see values that are smaller than x. smaller than or equal to x, right?
Yeah, I apologize.
Which cannot be its successor at all, right? Right?
No.
Okay. So here you can see that so we can totally forget about its left child. Okay. So we shouldn't even think about its left child. Whereas this node does not have a right child. Okay. So it seems that here it does not have a right child, and we cannot go to its left child. So where can we go?
So if if x doesn't have a right, we could just go straight to the root. That's going to be the only one that's going to be larger.
Sorry,
That's the only one that's going to be like larger than that value. If there's no.
Yes. Okay. No, it's not necessarily the root. So here so if it does not have a right child, if the node x does not have a right child, we can only go up. We cannot go down so it does not have a right child. We can totally ignore its left child when searching for its successor. So the only way that we can go is to go up. Okay. So here let's say let's just go one step up. Okay, let's go to this node. Let's go to this node. Okay, so is this node the successor of x?
No.
No. The reason is that when we are going up, we are basically going left and up, right? We're going left and up, correct? We're going this way rather than this way. We're going this way, correct? Not this way. When we go up, there are basically two ways for us to go. Either go up left or go up right. So here we're going up left. When we are going up left, what does that mean? What does that mean? It means based on the binary search tree property, we are observing a value that is smaller than or equal to x, right? Because well, if we go up left, if we go up left, then the value that we see, so basically x is going to be larger than the value that basically x is going to be larger than its parent, correct?
Correct.
Yes. So okay, so then there's no chance for this node to be the successor of x, because we're looking for a node who holds a value that is larger than x. Okay, so then this wouldn't work. So then let's go one more. Let's go up for one more step. Again, we are going up and left. So it means that we are only going to see a value that is even smaller, right?
Yeah.
Okay, and then so then let's go one more step up, and here this is the first time that we make a right and up turn, right? Okay, so what does that mean? If we go right and up, what does that mean?
That is going to be larger.
Yes, this value that we see y is going to be larger than or equal to all the values over this area, including x, correct?
Correct.
So this is basically the first node that we see that has a larger value than x. Then this is its successor. Okay. Is that clear?
Yes.
Okay. So then the else, so the else is pretty easy for us to write. If x does not have a right child, else what we do is that we keep going up until we make a right up turn. Okay, So we keep going up until we make the first right upturn. Make sense?
Yes.
Okay, cool. So then this is basically the logic behind the successor algorithm. And then let's look at the pseudocode. So here is this. Okay, if x dot right is not nil, return the minimum function at x dot right. So this is exactly the same as what we discussed for the first case. If x has a right child, we call the minimum function over the right child of x. Right?
Yes.
Yes. So then I don't think we need to explain this part. It's pretty straightforward. If you understand our previous logic, then this case is pretty straightforward. Okay, so what I'm going to mainly focus on is the second part. Okay, so here is this. Okay, so otherwise, if x dot right is nil, so what do we do? What do we do? So here it does not have a else, because we don't need to have a else, because if it's true, then it will just return this one, and the function already terminated. And if we go to execute the line 3, it means that x does not have a right child. Correct?
Yeah. Can you say that one more time?
Okay. So here you can say that previously what we discussed is that if x has a right child, we call the minimum function over x dot right. Else we keep going up until we make a right turn. Okay. So here you can see that over here we got a else, but in a pseudocode provided by the book, there is no else. Do you know why there is no else?
Because you have the while, so you just keep on going to the right.
No. The reason is because of this return. Okay. So if this is true, if x dot have a right child, then we'll just go to call the minimum function over its right child, and then return, meaning that we are going to stop the execution of the function over there. Right? So
okay.
if x has a right child, then there is no chance for us to go to execute line 3. Correct?
Yeah.
Okay. If we go to execute line 3, it only means that x does not have a right child. It only means else. Correct?
Yeah, that makes sense.
Yeah. So then there is no need for us to put this else, even though you're free to write a else statement and put everything like from line 3 inside the else part. It's fine. But they're just equivalent.
Okay.
Okay. So here, let's say what do we do with the from line 3 to line to line 7? Okay. So here, what it says is that so here, let's say we have x over here. X is the node x. Okay. So let's say we have y equal to x dot p. This is x, and x does not have a right child, so we are able to execute line 3. So we have y equal to x dot p. What does p mean?
That's the parent.
Yes, parent node. Okay, what is the parent node of x?
7.
Yes, the node that holds the value 7. So this is y. We have y over here. While y is not nil, and x equal to y dot right, y equals y dot right. Sure, let's say is y nil?
No.
No. And is this true? So basically this is true. And what about this? X equal to y dot right. So is this true of us?
That's true.
True. This is also true. If here, okay. So here, if I tell you this, okay, if we got two nodes, y and x, if I tell you, okay, x is, if x is, and they're just, so y is the parent of x. What we know is that y is the parent of x, okay? Y is the parent of x. If x equal to y dot right, what does that mean? It means that x is y's right child, correct? It means x is y's right child, correct?
Correct.
Yes. So x is y's right child, and if x is y's right child, and if we just say, okay, we go up from x to y. If we just go up from x to y, do we make a left turn or right turn? Do we go left or go right?
Can you say that one more time? I'm sorry.
Okay, if x is on the right hand side, if this, okay, let me just write it clear. If y is x dot p, and if y is the parent of x, and x is y's right child, okay, and if x is y's right child, okay, so if we go from x to y, do we make a up left or up right? If we
Left.
move, yes, okay, yes, if we move from x to y, we are making a left turn, right?
Yeah. Yes.
Okay, so can we rewrite it in this way? While we are going up left, while we are going up left, okay, so we basically say, okay, if we can just translate this condition as well, we go up left. We have x dot y and y equal to y dot p. So what do we do with that? Let me use a different color. So we have x equal to y, so I'm going to mark x over here, and then y equal to y dot p. So what is y dot p?
It would be the parent of the y, so it would be the parent of 7.
Yes, then it will be this node, right? Correct?
Right.
Okay, so what we do in these two lines is that we basically we are just going up by one level, correct? So we move x up by one level, and also we move y up by one level. Correct?
Correct.
So then can we say translate this while loop in this way? Okay, while we are going up left, we just move up.
Right.
Okay, and let's say, okay, so here this is what we have so far, and then let's say this is x and this is y. If this is x and this is y, okay, so so let's say if this is true or not. If is y nil, or is this true? Right over here, is this true?
Yes.
Yes, y is not nil, so this is true. Is x equal to does x equal to the right of y? Or is
Yes.
x the right child of y? Yes, this is also true. So this is true and true again. So it means that when we go up, we also make a left upturn. Okay, so then let's just keep going up. So then we have x equal to x dot y. X equal to y. So we're going to set x over here, and y equal to y dot p. Y dot parent is basically the root node. Okay, so Okay, so this is what we do with here. And okay, so next, let's come back to the value. Let's say if this is true or not. Is y new? Is y new?
No.
No.
No. So this is true, right?
Right.
And is x equal to y dot right?
That's false.
Yes, this is false. Okay, so and then we're going to terminate the value and then return y. This is the node that we're going to return, and it is the successor of the node that holds the value 13, right? Correct?
Right.
So here, basically what we do is that while we are going up left, we just move one level up. And if, okay, so here, keep going up until we make a right up turn. Are they equivalent?
Yes.
Hey, Professor, I do have a question.
Sure.
If we get to the stage where we have to implement the else or the while, whichever the case may be, why can't we just automatically designate the successor, the root, since we know that this one has no right children, so it's not going to be bigger. There's no bigger option. And then obviously the parent's not going to be bigger if it's on the right side. And that's the same for the next parent, the grandfather, I guess you could say. So why wouldn't you automatically set it the successor to the root? Why would you?
Oh, this is because you know it because you already see the example of the tree. If I give you a tree that I don't like you to look at the details of the tree, and I just say, okay, give you a random node of the tree, find the successor for me.
Yeah, then you need, okay. All right.
And you will need this process, right?
Mm-hmm.
Okay. So here, let's say, are these two sentences equivalent? Keep going up until we make a right up turn, or while we are going up left, we keep going up. Are they equivalent?
Yes, but Professor, I also have a question.
Sure.
If I can. So what if you start at 13 and you go 13, 7, 6, but in between 6 and 15 there's like 12 or like another number like that, or like 14 that you don't.
Okay, so okay.
You're going up
Your
to the right,
question
but
is
it's not
this.
bigger
Okay,
than 13.
so, okay, we got a very good question. If we got something like this, so let's say 12, and then 6, and then 7. So let me say. So actually, this node, so the node in between 12 and 6 cannot be, in between 6 and 15 cannot be 12, because if it's 12, then we cannot put 13 over here, because all the values to the left of this node should be less than it. So 13 is larger than it. So the only possible value is 14, right? You got me?
Kind of.
Okay, so here, let's say
yeah, I got
we
you.
replace this with 12, then this will not be a binary search tree, because so if for it to be a binary search tree, then all the values to the left or in the left subtree of this node should be less than or equal to that. But here we got 13, which is larger than it. So it cannot be 13, and so instead the only value it can be is 14. Okay, so if it's 14, then then the process for us to find the success of this node is like we go one up left, and we stop after we make the first right turn. This is its successor.
Okay, so 14 is the successor. Gotcha.
Yes. So as I said, we just keep going up until we make a right upturn, and then we stop over there. So that is the successor of the node of X. right?
Right, got it. Thank you.
No problem. Any other question?
No questions.
It says you're muted.
How about now?
Yeah.
Yeah.
no.
Okay.
It's good.
Thank you. So it seems that my my iPad Pro was just stuck. So okay. So cool. Okay. So thank you. So here my question is this. Okay, if say you understand the successor function, then so what is the complexity of that?
Would it also be O?
Yes, it's also OH. The reason is that, so at a certain node X, we either go down or go up. And at most H levels, we will move at most H levels. So so that's why we got the OH complexity for the successor function. It's also OH, where H is the height of the tree. Make sense?
Yeah.
Okay, cool. So then this is what we talked about, the OH complexity. And then let's look at the insertion function for binary search tree. So okay, this is the insertion function, and seems really complicated, but actually the way for us to do insertion is quite similar, as it's very similar to search. So let's say here I'm just going to draw an example. Okay, so suppose that we have this binary tree, and is this a binary search tree?
Yes.
Yeah.
Yes. Okay, so this is a binary search tree, and suppose here I said, okay, we got one new node to insert, which holds the value, let's say 13. Okay, we got a new node 13, to insert into this binary search tree? Where do you want to place this binary search? Where do you want to place this new node?
On the right subtree?
Yes. So we will start from the root of the tree and then we go right because the value is larger than the value is larger than that. Okay. And then so after we reach this node, okay, so where should we go?
Should go to the left.
Yes, we should go to the left. And then we reach this node. And where should we go?
To the left again.
Yes. And here, because we observe that, so we should put this, we should insert the node 13 to the left of this node. And fortunately, this node does not have a left child. It means that there is a free space for us to use over here. And that is the place for us to put the new node 13. Make sense?
Yeah.
Yeah. And here you can say that this process is pretty similar to search for the node 13, right? So search for the value 13. We start from the root, turning right, turning left, turn left. And so then until we reach a new, we reach an empty node. So here originally this node was empty because 15 does not have the node 15 does not have a left child. So until here we will stop. We will stop only if we reach a new node. And then we know that this is the place where should we insert the new node. Okay, so then this is the logic behind insert. And then let's look at the example over here. So let me redraw the example a little bit so it looks better for you when we go through the pseudocode. Should be 18. Okay, so suppose that we have this tree and we got a new node z over here, which holds the value 13. Okay, z is so here the insertion function takes two parameters. T is the tree and z is the new node to be inserted. So first we have y equal to new. We have y equal to new and x equal to t dot root. Okay, what is the root of the tree?
12.
Yes, the node that holds the value 12. So we have x over here, and then we have y as new. So far, let's just put y over here, y as new. But it will be clear for you. So what is the relationship between x and y? Think about it. So if x is the root node and y is new, if I tell you that there must be a close relationship between x and y, so what can you think about?
That y would be like the parent of x?
Yes, y is the parent of x because the root node, if you remember in last lecture, we said that only the root node does not have a parent or have a neo parent. So here, that's pretty good. I'm put y over here and I'm going to use dotted circle to denote that this is neo. Okay, y is the parent of x and we're going to maintain this parent and child relationship between x and y throughout the process. So while x is not neo, so obviously x is not neo, so we have y equal to x. So we're going to have y equal to x. We're going to move y down to x to its child. And then if z dot key is less than x dot key. So here we got z dot key as 13. And what is x dot key?
It's just the root. 12.
It's just the value stored at the root. It is 12. So this is false, right? So then we should go to else. We have x equal to x dot right. So we are going to move x to its right child. So we're going to move x right over here. So this is like we are basically moving both x and y down by one level, whereas we remain y remains the parent of x. Correct?
Yeah.
Okay. So if we want to summarize this part with one sentence, it's like move down. Move x and y down by one level. Okay. So while x is not new, while we don't see a new node, while we don't see a new node, we just move x and y down by one level. So okay, so this is what we have done. So for now we got x and y over here in these two places, and then so we go back to the while loop. X is not new, so we have y equal to x again. So we're going to move x. Oh, sorry, we're going to move y down by one level, and then we're going to compare the key between z and x. So here z dot key is still 13, whereas x dot key is 18. So then this is true, right?
Yeah, that's true.
Yes.
Okay,
Sure.
so then we're going to move x to its left child. So we are going to have x over here. So here you can see that again, we move both x and y down by one level. Okay, so so this is what we have, x and y, and then so we go back to the while loop. X is not new, so then we have y equal to x. We have y as x, so then we are going to move y down by one level, and then compare the key between z and x. Z dot key remains unchanged, and whereas x dot key is 15. So again, this is true. So we're going to move x to its left child. So x goes to its left child. This is x, which is a new node. Okay, so okay, then we go back to the while loop. Here we say that this condition fails, right? It's false because x is a new node. So then we should stop, correct?
Yeah, because it's equal to nil.
Yes, we should terminate the while loop. So then here, as previously we discussed, this is the place for the new node z. Okay, we should put z over here, and that so the following operation is to put z at x, the location of x. Okay, so we have this. So we have z dot p equal to y. So this is because, okay, y is the parent of x, and we know that we should move z over here. So basically after the move, z should be so y should be the parent of z, correct? Correct?
Yeah.
Okay, so with that operation, it's like z is claiming that this is my parent. This is claiming that this y is my parent. Z host value, okay? But what is unclear is that what is unclear to y is that y does not know if z should be its left child or right child. Only z knows, okay, y is my parent, but y does not know so whether z should be its left child or right child. So the next part of the code, the if and else, will help us to know, okay, so what is so whether z should be on the left side or right side of y. So here, let's say if y equal to nil, so what does that mean if y is nil? if y is new, what does that mean?
The tree is empty or was empty.
Yes, the tree is empty. It means this, okay? Remember, in the beginning of this process, we have y as this. We have y as the parent of x, whereas x is the root node, okay? So if y is new, it means that we never execute the while loop. We never move them down. Then the only condition for this for us to never execute the while loop is because here the x is also new, meaning that we got a tree that whose root node is also empty. Basically, we got an empty tree. So if we want to insert a new node, a node into an empty tree, then the new node should be the root of the tree, correct? Okay, if we got a tree that is empty, and then we inserted the first node into the tree. So should this node be the root of the tree?
The one that you want to insert would be the root?
Yes.
Assuming that there is no root, that it's empty completely, then
yes.
It would be, well, technically it would be because it's the only one. Right?
Yes, because after the insertion, the new node is basically the only node in the tree, so it has to be the root.
Mm.
It's like if we got no faculty in our department, and so far the department just hired me, automatically I'm the chair of the department. Correct?
Yeah, by default, it would be correct.
Yes. So that's the case. So if y is new, it means that the tree is empty. Okay, it means if the tree is empty, then the new node z should be the root of the tree. Okay, so otherwise, if z dot key is less than y dot key, okay, so basically here we're comparing the relationship between z and its parent y. So if z dot key is less than y dot key, then we know that z should be the left child of y. So that's why we have this. Otherwise, we should make z as the right child of y. So in our case, we have z dot key as 13 and y dot key as 15. So this is true. So then, so y is going to declare z as its left child. So it's like this. So this is how we finish the insertion of the new node z. Make sense?
Yeah. Professor, quick question. If you're the number that you're trying to insert, if it is equal to, let's say, one of the tree integers that are already inside of it, what would you do? Like, let's say
we still move down. We are only going to stop so here basically say if the new value is less than an existing value, we go left. Otherwise, even though it is equal, we go right.
Okay, so let's say like if we had 18, though, it would still go right though?
Yes.
Would we consider a right
so
check?
Here, if we want to insert a new node that holds the value 18, we start from the root, move to this node, and then we also move to this node. And then we will put 18 to the left of this node.
Oh, okay, yeah, okay.
Yeah. Okay. Cool, this is a very good question. And so any other question for me? No? Okay, so then what is the complexity of the insertion function?
Big O of H again? Yeah.
Yes, OH again, because we are going to move X and Y at most H levels in a tree. So because this process is pretty much like the search, and also so search also has a OH complexity. So this is also OH. Okay, so this is what we discussed so far, and any question for the insertion function? Oh, okay, so then I'm going to briefly talk about the last function named delete. Okay, so it's really complicated, and so so here, suppose that we have a node z in a tree and we want to remove it, and depending on the case, so here, if this is the node that we want to remove, if z is the node that we want to remove, the simplest case is that z does not have any child. Okay, if z does not have any child, then it's pretty simple. We just let's let y be the parent of z. We just say okay. This its parent has if z is the left child of its parent, then we are going to say y dot left equal to nil. So in that case, it's like we exclude this node z from the tree, correct? Do you get me? Okay, I'm going to give an example which is not appropriate at all, but just because I just want to make it a little bit clear for you. So suppose this is your family tree, and this is your parent, and say one day you offended your parent so much, and then your parents say, okay, I'm not. So your family wants to remove you from your family. Okay, so exclude you from the family. This is you. This is you. And if you do not have any kids, then it's really simple. Okay, so your parent is going to say, I don't have this child, by saying by filling your place with me, saying that I don't have that child. Got me?
Yeah.
Yeah, I got you.
Yeah, I don't want to offend you, but I think it's easier to explain. So okay, so this is one way. Okay, so then so this is the simplest case, no child. Okay, if it only has one child, only left child, if this node z only has one left child, but no right child. Okay, so it's also going to be relatively simple. We're going to let this child, its left child, take the position of itself. Okay, so it's going to be something like this, right? Only left, if there is only one left child, like what I showed you over here, we're going to let its left child claim the place of z, right? And another case is that if it only has one, it only has a right child but no left child, then it's going to be similar. We're going to let its right child substitute its place. It's like, so this is like in my home country, like 30 years or 40 years ago. The thing is that, so if your father retires, you will get the chance to inherit his position by default. So yes, so that is pretty much like so if you live in that society, and if your parents say, okay, I'm going to retire, then if you are the only child, then so the only child just goes to replace his position, take over his position. Make sense?
Yeah.
Okay, so the most complicated case comes from here. Okay, if the node z has both a left and a right child, then it's really complicated. If it has both left and the right child, so then this is this is the process. So okay, so it will go to its right child. It will go to its right subtree and find the minimum node. Find the minimum node, and then let the minimum node take over the place of Z. Okay, so this is the process. Okay, so basically we will find the minimum node at its right subtree and then let it take over the place of Z. Make sense? Sorry, I need to open up the door for my wife. Just 1 second, okay? Okay, so yes, this is the process. Find them. This is like if your parent retires, and your parent has a lot of kids, and your kids, so also some grandchildren, so your parent will pick the youngest descendant and then take over its place. Yes, so this is the logic behind that, and the code. This is the complete code of the deletion function. It's really complicated for you to implement. So in your homework 5, I don't require you to do that. So this is not required at all. Okay. Any question for me?
No questions.
Okay, sure. So this is the new material that we need to discuss as of today. So so starting from today, you can fully work on your homework 5, which is to implement the six functions of binary search tree. I think all of them are doable, are not too difficult. They're not too difficult at all. So and based on the emails that I received from last week, so last week I received an email asking me what is the correct output of homework 4. Okay, so of homework 4. So actually this is the only email that I didn't reply, because I'm not supposed to tell you what is the correct output. So, and actually for all the homeworks, if you want to know what is the correct output, you can infer it either by yourself or go to the slides and find the answer. For homework 4, for example, if we look at the stack, the stack, so part, I'm going to open up my Eclipse on my, so I'm going to show it to you on my laptop. Okay, so here, so let me open up my Eclipse. Okay, the training finish. Take a long time for me to open up my, okay, here it is. So can you see my screen?
Yeah, we can see your screen.
Okay, sure. If we look at this is the skeleton code that I provide to you for stack. So if we look at stack, so first what we do is that we create a if you look at the main function, what you can say is that first we create a stack which in total have 10 spaces, and So for I from 0 to and I is less than 5, we are going to push the value I. So after this process, what do you think that the stack, what kind of value do you think that the stack is going to have?
Should have values from 0 to 4.
Yes, from 0 to 4. And then, so after this, so next, let's say how many times do we pop with in the last for loop? We pop twice, right? Correct?
Yep. Yeah.
Okay. So in the first pop, which value did we remove?
4.
Yes, because stack follows last in, first out policy. 4 enters the stack last, so it goes out first. And which value do we remove in a second pop?
3.
Yes. So yes. So if you figure it out, I mean from the main function, and if you understand the logic of stack, then so you can easily interpret what is the correct output. Okay. So I hope that in the future you can do this by yourself. I know that when you finish your coding, you desperately want to check if your output is correct or not. But in our homeworks, I'm not going to explicitly tell you what is the correct one. So because if you understand the lecture pretty well, it's pretty easy for you to infer it by yourself. Okay, so any other question for me for today? Okay, so if no, then that's the end of our lecture for today. So then we will have a relatively lightweight lecture this Friday. Okay, so have a good one.
Have a good one, Professor.
Yeah, homework 5 is due next week. Oh, Yuri, are you still here? I just find this question. Okay, so then probably I will contact this student later. Hamad.